knowledge that often exceeds a model's context window. For example, code copilots might need access to entire codebases, and research assistants may need to analyze multiple books. Originally developed to overcome a model's context limitations, RAG also enables more efficient use of Informa tie-in, improving response quality while reducing costs. From the early days of foundation models, it was clear that the RAG pattern would be immensely valuable for a wide range of applications, and it has since been rapidly adopted across both consumer and enterprise use cases. RAG employs a two-step process. It first retrieves relevant information from external memory and then uses this information to generate more accurate responses. The success of a RAG system depends on the quality of its retriever. Term-based retrievers, such as Elasticsearch and BM25, are much lighter to implement and can provide strong baselines. Embedding-based retrievers are more computationally intensive but have the potential to outperform term-based algorithms. Embedding-based retrieval is powered by vector search, which is also the backbone of many core internet applications such as search and recommender systems. Many vector search algorithms developed for these applications can be used for RAG. The RAG pattern can be seen as a special case of agent where the retriever is a tool the model can use. Both patterns allow a model to circumvent its context limitation and stay more up-to-date, but the agentic pattern can do even more than that. An agent is defined by its environment and the tools it can access. In an AI-powered agent, AI is the planner that analyzes its given task, considers different solutions, and picks the most promising one. A complex task can require many steps to solve, which requires a powerful model to plan. A model's ability to plan can be augmented with reflection and a memory system to help it keep track of its progress. The more tools you give a model, the more capabilities the model has, enabling it to solve more challenging tasks. However, the more automated the agent becomes, the more catastrophic its failures can be. Tool use exposes agents to many security risks discussed in Chapter 5. For agents to work in the real world, rigorous defensive mechanisms need to be put in place. Both RAG and agents work with a lot of information, which often exceeds the maximum context length of the underlying model. This necessitates the introduction of a memory system for managing and using all the information a model has. This chapter ended with a short discussion on what this component looks like. Summary, 305. RAG and agents are both prompt-based methods, as they influence the model's quality solely through inputs without modifying the model itself. While they can enable many incredible applications, modifying the underlying model can open up even more possibilities. How to do so will be the topic of the next chapter. 306, Chapter 6, RAG and Agents. Chapter 7, Fine-tuning. Fine-tuning is the process of adapting a model to a specific task by further training the whole model or part of the model. Chapters 5 and 6 discuss prompt-based methods, which adapt a model by giving it instructions, context, and tools. Fine-tuning adapts a model by adjusting its weights. Fine-tuning can enhance various aspects of a model. It can improve the model's domain-specific capabilities, such as coding or medical question answering, and can also strengthen its safety. However, it is most often used to improve the model's instruction-following ability, particularly to ensure it adheres to specific output styles and formats. While fine-tuning can help create models that are more customized to your needs, it also requires more upfront investment. A question I hear very often is when to fine-tune and when to do RAG. After an overview of fine-tuning, this chapter will discuss the reasons for fine-tuning and the reasons for not fine-tuning, as well as a simple framework for thinking about choosing between fine-tuning and alternate methods. Compared to prompt-based methods, fine-tuning incurs a much higher memory footprint. At the scale of today's foundation models, naive fine-tuning often requires more memory than what's available on a single GPU. This makes fine-tuning expensive and challenging to do. As discussed throughout this chapter, reducing memory requirements is a primary motivation for many fine-tuning techniques. This chapter dedicates one section to outlining factors contributing to a model's memory footprint, which is important for understanding these techniques. A memory-efficient approach that has become dominant in the fine-tuning space is PEFT, parameter-efficient fine-tuning. This chapter explores PEFT and how it differs from traditional fine-tuning. This chapter also provides an overview of its evolving 307 techniques. I'll focus particularly on one compelling category, adapter-based techniques. With prompt-based methods, knowledge about how ML models operate under the hood is recommended but not strictly necessary. However, fine-tuning brings you to the realm of model training, where ML knowledge is required. ML basics are beyond the scope of this book. If you want a quick refresh, the book's GitHub repository has pointers to helpful resources. In this chapter, I'll cover a few core concepts immediately relevant to the discussion. This chapter is the most technically challenging one for me to write, not because of the complexity of the concepts, but because of the broad scope these concepts cover. I suspect it might also be technically challenging to read. If, at any point, you feel like you're diving too deep into details that aren't relevant to your work, feel free to skip. There's a lot to discuss. Let's dive in. Fine-tuning overview. To fine-tune, you start with a base model that has some, but not all, of the capabilities you need. The goal of fine-tuning is to get this model to perform well enough for your specific task. Fine-tuning is one way to do transfer learning, a concept first introduced by Bozanovsky and Fulgosi in 1976. Transfer learning focuses on how to transfer the knowledge gained from one task to accelerate learning for a new, related task. This is conceptually similar to how humans transfer skills. For example, knowing how to play the piano can make it easier to learn another musical instrument. An early large-scale success in transfer learning was Google's multilingual translation system, Johnson et al., 2016. The model transferred its knowledge of Portuguese, English and English-Spanish translation to directly translate Portuguese to Spanish, even though there were no Portuguese-Spanish examples in the training data. Since the early days of deep learning, transfer learning has offered a solution for tasks with limited or expensive training data. By training a base model on tasks with abundant data, you can then transfer that knowledge to a target task. For LLMs, knowledge gained from pre-training on text completion, a task with abundant data, is transferred to more specialized tasks, like legal question answering or text-to-SQL, which often have less available data. This capability for transfer learn ing makes foundation models particularly valuable. 308, Chapter 7, Fine-tuning. Transfer learning improves sample efficiency, allowing a model to learn the same behavior with fewer examples. A sample-efficient model learns effectively from fewer samples. For example, while training a model from scratch for legal question answer ing may need millions of examples, fine-tuning a good base model might only require a few hundred. Ideally, much of what the model needs to learn is already present in the base model, and fine-tuning just refines the model's behavior. OpenAI's InstructGPT paper, 2022, suggested viewing fine-tuning as unlocking the capabilities a model already has but that are difficult for users to access via prompting alone. Fine-tuning isn't the only way to do transfer learning. Another approach is feature-based transfer. In this approach, a model is trained to extract features from the data, usually as embedding vectors, which are then used by another model. I mentioned feature-based transfer briefly in Chapter 2, when discussing how part of a foundation model can be reused for a classification task by adding a classifier head. Feature-based transfer is very common in computer vision. For instance, in the second half of the 2010s, many people used models trained on the ImageNet dataset to extract features from images and use these features in other computer vision tasks such as object detection or image segmentation. Fine-tuning is part of a model's training process. It's an extension of model pre-training. Because any training that happens after pre-training is fine-tuning, fine-tune ing can take many different forms. Chapter 2 already discussed two types of fine-tuning, supervised fine-tuning and preference fine-tuning. Let's do a quick recap of these methods and how you might leverage them as an application developer. Recall that a model's training process starts with pre-training, which is usually done with self-supervision. Self-supervision allows the model to learn from a large amount of unlabeled data. For language models, self-supervised data is typically just sequences of text that don't need annotations. Before fine-tuning this pre-trained model with expensive task-specific data, you can fine-tune it with self-supervision using cheap task-related data. For example, to fine-tune a model for legal question answering, before fine-tuning it on expensive annotated question, answer, data, you can fine-tune it on raw legal documents. Similarly, to fine-tune a model to do book summarization in Vietnamese, you can first fine-tune it on a large collection of Vietnamese text. Self-supervised fine-tuning is also called continued pre-training. Fine-tuning overview 309. As discussed in Chapter 1, language models can be autoregressive or masked. An autoregressive model predicts the next token in a sequence using the previous tokens as the context. A masked model fills in the blank using the tokens both before and after it. Similarly, with supervised fine-tuning, you can also fine-tune a model to predict the next token or fill in the blank. The latter, also known as infilling fine-tuning, is especially useful for tasks such as text editing and code debugging. You can fine-tune a model for infilling even if it was pre-trained autoregressively. The massive amount of data a model can learn from during self-supervised learning outfits the model with a rich understanding of the world, but it might be hard for users to extract that knowledge for their tasks, or the way the model behaves might be misaligned with human preference. Supervised fine-tuning uses high-quality annotated data to refine the model to align with human usage and preference. During supervised fine-tuning, the model is trained using input-output pairs. The input can be an instruction and the output can be a response. A response can be open-ended, such as for the task of book summarization. A response can be also close-ended, such as for a classification task. High-quality instruction data can be challenging and expensive to create, especially for instructions that require factual consistency, domain expertise, or political correctness. Chapter 8 discusses how to acquire instruction data. A model can also be fine-tuned with reinforcement learning to generate responses that maximize human preference. Preference fine-tuning requires comparative data that typically follows the format: instruction, winning response, losing response. It's possible to fine-tune a model to extend its context length. Long context fine-tuning typically requires modifying the model's architecture, such as adjusting the positional embeddings. A long sequence means more possible positions for tokens, and positional embeddings should be able to handle them. Compared to other fine-tuning techniques, long context fine-tuning is harder to do. The resulting model might also degrade on shorter sequences. Figure 7.1 shows the making of different code llama models, Rozier et al., 2024, from the base model Llama 2, using different fine-tuning techniques. Using long context fine-tuning, they were able to increase the model's maximum context length from 4,096 tokens to 16,384 tokens to accommodate longer code files. In the image, instruction fine-tuning refers to supervised fine-tuning. Fine-tuning can be done by both model developers and application developers. Model developers typically post-train a model with different fine-tuning techniques before releasing it. A model developer might also release different model versions, each fine-tuned to a different extent, so that application developers can choose the version that works best for them. 310, Chapter 7, Fine-tuning. Figure 7.1. Different fine-tuning techniques used to make different code llama models. Image from the Rozier et al. 2024, adapted from an original image licensed under CC by 4.0. As an application developer, you might fine-tune a pre-trained model, but most likely, you'll fine-tune a model that has been post-trained. The more refined a model is and the more relevant its knowledge is to your task, the less work you'll have to do to adapt it. When to fine-tune before jumping into different fine-tuning techniques, it's necessary to consider whether fine-tuning is the right option for you. Compared to prompt-based methods, fine-tuning requires significantly more resources, not just in data and hardware, but also in ML talent. Therefore, fine-tuning is generally attempted after extensive experiments with prompt-based methods. However, fine-tuning and prompting aren't mutually exclusive. Real-world problems often require both approaches. Reasons to fine-tune. The primary reason for fine-tuning is to improve a model's quality, in terms of both general capabilities and task-specific capabilities. Fine-tuning is commonly used to improve a model's ability to generate outputs following specific structures, such as JSON or YAML formats. A general-purpose model that performs well on a wide range of benchmarks might not perform well on your specific task. If the model you want to use wasn't sufficiently trained on your task, fine-tuning it with your data can be especially useful. For example, an out-of-the-box model might be good at converting from text to the standard SQL dialect but might fail with a less common SQL dialect. In this case, fine-tuning this model on data containing the SQL dialect will help. Similarly, if the model works well on standard SQL for common queries but often fails for customer-specific queries, fine-tuning the model on customer-specific queries might help. When to fine-tune. 311. 1. Some people call this phenomenon an alignment tax, by et al., 2020, but this term can be confused with penalties against human preference alignment. One especially interesting use case of fine-tuning is bias mitigation. The idea is that if the base model perpetuates certain biases from its training data, exposing it to carefully curated data during fine-tuning can counteract these biases. Wang and Rusakovsky, 2023. For example, if a model consistently assigns CEOs male-sounding names, fine-tuning it on a dataset with many female CEOs can mitigate this bias. Garimella et al. 2022 found that fine-tuning BERT-like language models on text authored by women can reduce these models' gender biases, while fine-tuning them on texts by African authors can reduce racial biases. You can fine-tune a big model to make it even better, but fine-tuning smaller models is much more common. Smaller models require less memory, and, therefore, are easier to fine-tune. They are also cheaper and faster to use in production. A common approach is to fine-tune a small model to imitate the behavior of a larger model using data generated by this large model. Because this approach distills the larger model's knowledge into the smaller model, it's called distillation. This is discussed in Chapter 8 together with other data synthesis techniques. A small model, fine-tuned on a specific task, might outperform a much larger out-of-the-box model on that task. For example, Grammarly found that their fine-tuned FLAN T5 models, Chung et al. 2022, outperformed a GPT-3 variant specialized in text editing across a wide range of writing assistant tasks despite being 60 times smaller. The fine-tuning process used only 82,000 instruction output pairs, which is smaller than the data typically needed to train a text editing model from scratch. In the early days of foundation models, when the strongest models were commercial with limited fine-tuning access, there weren't many competitive models available for fine-tuning. However, as the open-source community proliferates with high-quality models of all sizes, tailored for a wide variety of domains, fine-tuning has become a lot more viable and attractive. Reasons not to fine-tune. While fine-tuning can improve a model in many ways, many of these improvements can also be achieved, to a certain extent, without fine-tuning. Fine-tuning can improve a model's performance, but so do carefully crafted prompts and context. Fine-tuning can help with structured outputs, but many other techniques, as discussed in Chapter 2, can also do that. First, while fine-tuning a model for a specific task can improve its performance for that task, it can degrade its performance for other tasks. This can be frustrating when you intend this model for an application that expects diverse prompts. 312 Chapter 7, Fine-tuning. Imagine you need a model for 3 types of queries: product recommendations, changing orders, and general feedback. Originally, the model works well for product recommendations and general feedback but poorly for changing orders. To fix this, you fine-tune the model on a dataset of query, response, pairs about changing orders. The fine-tuned model might indeed perform better for this type of query, but worse for the 2 other tasks. What do you do in this situation? You can fine-tune the model on all the queries you care about, not just changing orders. If you can't seem to get a model to perform well on all your tasks, consider using separate models for different tasks. If you wish to combine these separate models into one to make serving them easier, you can also consider merging them together, as discussed later in this chapter. If you're just starting to experiment with a project, fine-tuning is rarely the first thing you should attempt. Fine-tuning requires high upfront investments and continual maintenance. First, you need data. Annotated data can be slow and expensive to acquire manually, especially for tasks that demand critical thinking and domain expertise. Open-source data and AI-generated data can mitigate the cost, but their effectiveness is highly variable. Second, fine-tuning requires the knowledge of how to train models. You need to evaluate base models to choose one to fine-tune. Depending on your needs and resources, options might be limited. While fine-tuning frameworks and APIs can automate many steps in the actual fine-tuning process, you still need to understand the different training knobs you can tweak, monitor the learning process, and debug when something is wrong. For example, you need to understand how an optimizer works, what learning rate to use, how much training data is needed, how to address overfitting/underfitting, and how to evaluate your models throughout the process. Third, once you have a fine-tuned model, you'll need to figure out how to serve it. Will you host it yourself or use an API service? As discussed in Chapter 9, inference optimization for large models, especially LLMs, isn't trivial. Fine-tuning requires less of a technical leap if you're already hosting your models in-house and familiar with how to operate models. More importantly, you need to establish a policy and budget for monitoring, maintaining, and updating your model. As you iterate on your fine-tuned model, new base models are being developed at a rapid pace. These base models may improve faster than you can enhance your fine-tuned model. If a new base model outperforms your fine-tuned model on your specific task, how significant does the performance improvement have to be before you switch to the new base model? What if a new base model doesn't immediately outperform your existing model but has the potential to do so after fine-tuning? Would you experiment with it? When to fine-tune, 313. Too many businesses resist changing technologies they consider good enough. If all companies were quick to adopt more optimal solutions, fax machines would have become obsolete by now. 3. I've also noticed a few cases when engineers know that fine-tuning isn't strictly necessary but still insist on doing it because they want to learn how to fine-tune. As an engineer who likes learning new skills, I appreciate this mindset. However, if you're in a leadership position, it can be hard to differentiate whether fine-tuning is needed or wanted. 40314 denotes the date this GPT-4 version came out, March 14, 2024. The specific date stamp matters because different versions vary significantly in performance. In many cases, switching to a better model would provide only a small incremental improvement, and your task might be given a lower priority than projects with larger returns, like enabling new use cases. 2 AI engineering experiments should start with prompting, following the best practices discussed in Chapter 6. Explore more advanced solutions only if prompting alone proves inadequate. Ensure you have thoroughly tested various prompts, as a model's performance can vary greatly with different prompts. Many practitioners I've spoken with share a similar story that goes like this. Someone complains that prompting is ineffective and insists on fine-tuning. Upon investigation, it turns out that prompt experiments were minimal and unsystematic. Instructions were unclear, examples didn't represent actual data, and metrics were poorly defined. After refining the prompt experiment process, the prompt quality improved enough to be sufficient for their application. 3. Fine-tuning domain-specific tasks. Beware of the argument that general-purpose models don't work well for domain-specific tasks, and, therefore, you must fine-tune or train models for your specific tasks. As general-purpose models become more capable, they also become better at domain-specific tasks and can outperform the domain-specific models. An interesting early specialized model is Bloomberg GPT, which was introduced by Bloomberg in March 2023. The strongest models on the market then were all proprietary, and Bloomberg wanted a mid-size model that performed well on financial tasks and could be hosted in-house for use cases with sensitive data. The model, with 50 billion parameters, required 1.3 million GPU hours for training. The estimated cost of the compute was between $1.3 million and $2.6 million, excluding data costs, Wu et al., 2023. In the same month, OpenAI released GPT-4-0314. For research by Li et al. 2023 demonstrated that GPT-4-0314 significantly outperformed Bloomberg GPT across various financial benchmarks. Table 7.1 provides details of two such benchmarks. 314, Chapter 7, Fine-tuning. Table 7.1. General-purpose models like GPT-4 can outperform financial models in financial domains. Model FIQA Sentiment Analysis, Weighted F1, CONV FinQA, Accuracy, GPT-4-0314, 0-shot, 87. 1576. 48 Bloomberg GPT-75. 0743. 41 Since then, several mid-size models with performance comparable to GPT-4 have been released, including Claude 3. 5 Sonnet, 70B parameters, Llama 3-70B Instruct, and Qwen 2-72B Instruct. The latter two are open-weight and can be self-hosted. Because benchmarks are insufficient to capture real-world performance, it's possible that Bloomberg GPT works well for Bloomberg for their specific use cases. The Bloomberg team certainly gained invaluable experience through training this model, which might enable them to better develop and operate future models. Both fine-tuning and prompting experiments require systematic processes. Doing prompt experiments enables developers to build an evaluation pipeline, data annotate tie-in guideline, and experiment tracking practices that will be stepping stones for fine-tuning. One benefit of fine-tuning, before prompt caching was introduced, was that it can help optimize token usage. The more examples you add to a prompt, the more input tokens the model will use, which increases both latency and cost. Instead of including your examples in each prompt, you can fine-tune a model on these examples. This allows you to use shorter prompts with the fine-tuned model, as shown in Figure 7.2. With prompt caching, where repetitive prompt segments can be cached for reuse, this is no longer a strong benefit. Prompt caching is discussed further in Chapter 9. However, the number of examples you can use with a prompt is still limited by the maximum context length. With fine-tuning, there's no limit to how many examples you can use. When to fine-tune, 315. Figure 7.2. Instead of including examples in each prompt, which increases cost and latency, you fine-tune a model on these examples. Fine-tuning and RAG. Once you've maximized the performance gains from prompting, you might wonder whether to do RAG or fine-tuning next. The answer depends on whether your model's failures are information-based or behavior-based. If the model fails because it lacks information, a RAG system that gives the model access to the relevant sources of information can help. Information-based failures happen when the outputs are factually wrong or outdated. Here are two example scenario iOS in which information-based failures happen. The model doesn't have the information. Public models are unlikely to have information private to you or your organizer tie-in. When a model doesn't have the information, it either tells you so or hallucinates an answer. The model has outdated information. If you ask, how many studio albums has Taylor Swift released, and the correct answer is 11, but the model answers 10, it can be because the model's cutoff date was before the release of the latest album. The paper Fine-tuning or Retrieval, by Avadia et al. 2024, demonstrated that for tasks that require up-to-date information, such as questions about current events, RAG outperformed fine-tuned models. Not only that, RAG with the base model 316, Chapter 7, Fine-tuning. 5 Some people, such as the authors of the Llama 3. 1 paper, Dubé et al., 2024, adhere to the principle that post-training should align the model to know what it knows rather than add knowledge, outperformed RAG with fine-tuned models, as shown in Table 7.2. This finding indicates that while fine-tuning can enhance a model's performance on a specific task, it may also lead to a decline in performance in other areas. Table 7.2. RAG outperforms fine-tuning on a question-answering task about current events, curated by Avadia et al. 2024, FTREG and FTPAR refer to two different fine-tuning approaches the author used. Base model plus RAG FTREG FT par FTREG plus RAG FT par plus RAG Mistral 7B0. 481 0. 875 0. 504 0. 588 0. 810 0. 830 Llama 2-7B0. 353 0. 585 0. 219 0. 392 0. 326 0. 520 Orca 2-7B0. 456 0. 876 0. 511 0. 566 0. 820 0. 826 On the other hand, if the model has behavioral issues, fine-tuning might help. One behavioral issue is when the model's outputs are factually correct but irrelevant to the task. For example, you ask the model to generate technical specifications for a software project to provide to your engineering teams. While accurate, the generated specs lack the details your teams need. Fine-tuning the model with well-defined technical specifications can make the outputs more relevant. Another issue is when it fails to follow the expected output format. For example, if you ask the model to write HTML code, but the generated code didn't compile, it might be because the model wasn't sufficiently exposed to HTML in its training data. You can correct this by exposing the model to more HTML code during fine-tuning. Semantic parsing is a category of tasks whose success hinges on the model's ability to generate outputs in the expected format and, therefore, often requires fine-tuning. Semantic parsing is discussed briefly in chapters 2 and 6. As a reminder, semantic parsing means converting natural language into a structured format like JSON. Strong off-the-shelf models are generally good for common, less complex syntaxes like JSON, YAML, and regex. However, they might not be as good for syntaxes with fewer available examples on the internet, such as a domain-specific language for a less popular tool or a complex syntax. In short, fine-tuning is for form and RAG is for facts. A RAG system gives your model external knowledge to construct more accurate and informative answers. A RAG system can help mitigate your model's hallucinations. Fine-tuning, on the other hand, helps your model understand and follow syntaxes and styles. 5. While fine-tuning can potentially reduce hallucinations if done with enough high-quality data, it can also worsen hallucinations if the data quality is low. When to fine-tune, 317. If your model has both information and behavior issues, start with RAG. RAG is equally easier since you won't have to worry about curating training data or hosting the fine-tuned models. When doing RAG, start with simple term-based solutions such as BM25 instead of jumping straight into something that requires vector databases. RAG can also introduce a more significant performance boost than fine-tuning. Ovadia et al. 2024 showed that for almost all question categories in the MMLU benchmark, RAG outperforms fine-tuning for 3 different models, Mistral 7B, Llama 2-7B, and Orca 2-7B. However, RAG and fine-tuning aren't mutually exclusive. They can sometimes be used together to maximize your application's performance. In the same experiment, Ovadia et al. 2024 showed that incorporating RAG on top of a fine-tuned model can boost its performance on the MMLU benchmark 43% of the time. It's important to note that in this experiment, using RAG with fine-tuned models doesn't improve the performance 57% of the time, compared to using RAG alone. There's no universal workflow for all applications. Figure 7.3 shows some paths an application development process might follow over time. The arrow indicates what next step you might try. This figure is inspired by an example workflow shown by OpenAI, 2023. Figure 7.3. Example application development flows. After simple retrieval, such as term-based retrieval, whether to experiment with more complex retrieval, such as hybrid search, or fine-tuning depends on each application and its failure modes. So the workflow to adapt a model to a task might work as follows. Note that before any of the adaptation steps, you should define your evaluation criteria and design your evaluation pipeline, as discussed in Chapter 4. This evaluation pipeline is what you'll use to benchmark your progress as you develop your application. Evaluation 318, Chapter 7, Fine-tuning. Doesn't happen only in the beginning. It should be present during every step of the process. 1. Try to get a model to perform your task with prompting alone. Use the prompt engineering best practices covered in Chapter 5, including systematically versioning your prompts. 2. Add more examples to the prompt. Depending on the use case, the number of examples needed might be between 1 and 50. 3. If your model frequently fails due to missing information, connect it to data sources that can supply relevant information. When starting with RAG, begin by using basic retrieval methods like term-based search. Even with simple retrieval, adding relevant and accurate knowledge should lead to some improvement in your model's performance. 4. Depending on your model's failure modes, you might explore one of these next steps. A. If the model continues having information-based failures, you might want to try even more advanced RAG methods, such as embedding-based retrieval. B. If the model continues having behavioral issues, such as it keeps generating irrelevant, malformatted, or unsafe responses, you can opt for fine-tuning. Embedding-based retrieval increases inference complexity by introducing additional components into the pipeline, while fine-tuning increases the complexity of model development but leaves inference unchanged. 5. Combine both RAG and fine-tuning for even more performance boost. If, after considering all the pros and cons of fine-tuning and other alternate techniques, you decide to fine-tune your model, the rest of the chapter is for you. First, let's look into the number 1 challenge of fine-tuning, its memory bottleneck. Memory bottlenecks. Because fine-tuning is memory-intensive, many fine-tuning techniques aim to minimize their memory footprint. Understanding what causes this memory bottleneck is necessary to understand why and how these techniques work. This understanding, in turn, can help you select a fine-tuning method that works best for you. Besides explaining fine-tuning's memory bottleneck, this section also introduces formulas for back-of-the-napkin calculation of the memory usage of each model. This calculation is useful in estimating what hardware you'd need to serve or fine-tune a model. Memory bottlenecks 319. Because memory calculation requires a breakdown of low-level ML and computing concepts, this section is technically dense. If you're already familiar with these concepts, feel free to skip them. Key takeaways for understanding memory bottlenecks. If you decide to skip this section, here are a few key takeaways. If you find any of these takeaways unfamiliar, the concepts in this section should help explain it. 1. Because of the scale of foundation models, memory is a bottleneck for working with them, both for inference and for fine-tuning. The memory needed for fine-tuning is typically much higher than the memory needed for inference because of the way neural networks are trained. 2. The key contributors to a model's memory footprint during fine-tuning are its number of parameters, its number of trainable parameters, and its numerical representations. 3. The more trainable parameters, the higher the memory footprint. You can reduce memory requirement for fine-tuning by reducing the number of trainable parameters. Reducing the number of trainable parameters is the motivation for PEFT, parameter-efficient fine-tuning. 4. Quantization refers to the practice of converting a model from a format with more bits to a format with fewer bits. Quantization is a straightforward and efficient way to reduce a model's memory footprint. For a model of 13 billion parameters, using FP32 means 4 bytes per weight or 52 gigabytes for the whole weights. If you can reduce each value to only 2 bytes, the memory needed for the model's weights decreases to 26 gigabytes. 5. Inference is typically done using as few bits as possible, such as 16 bits, 8 bits, and even 4 bits. 6. Training is more sensitive to numerical precision, so it's harder to train a model in lower precision. Training is typically done in mixed precision, with some operations done in higher precision, e.g., 32-bit, and some in lower precision, e.g., 16-bit or 8-bit. Backpropagation and trainable parameters. A key factor that determines a model's memory footprint during fine-tuning is its number of trainable parameters. A trainable parameter is a parameter that can be updated during fine-tuning. During pre-training, all model parameters are updated. During inference, no model parameters are updated. During fine-tuning, some or all model parameters may be updated. The parameters that are kept unchanged are frozen parameters. 320 Chapter 7, Fine-tuning. 6. Other than backpropagation, a promising approach to training neural networks is evolutionary strategy. One example, described by Maheswaranathan et al., combines random search with surrogate gradients, instead of using real gradients, to update model weights. Another interesting approach is direct feedback alignment, Arild Nachland, 2016. 7. If a parameter is not trainable, it doesn't need to be updated and, therefore, there's no need to compute its gradient. The memory needed for each trainable parameter results from the way a model is trained. As of this writing, neural networks are typically trained using a mechanism called backpropagation. 6. With backpropagation, each training step consists of 2 phases. 1. Forward pass, the process of computing the output from the input. 2. Backward pass, the process of updating the model's weights using the aggregated signals from the forward pass. During inference, only the forward pass is executed. During training, both passes are executed. At a high level, the backward pass works as follows. 1. Compare the computed output from the forward pass against the expected output, ground truth. If they are different, the model made a mistake, and the parameters need to be adjusted. The difference between the computed output and the expected output is called the loss. 2. Compute how much each trainable parameter contributes to the mistake. This value is called the gradient. Mathematically, gradients are computed by taking the derivative of the loss with respect to each trainable parameter. There's one gradient value per trainable parameter. 7. If a parameter has a high gradient, it significantly contributes to the loss and should be adjusted more. 3. Adjust trainable parameter values using their corresponding gradient. How much each parameter should be readjusted, given its gradient value, is determined by the optimizer. Common optimizers include SGD, stochastic gradient descent, and ADAM. For transformer-based models, ADAM is, by far, the most widely used optimizer. The forward and backward pass for a hypothetical neural network with 3 parameters and 1 nonlinear activation function is visualized in Figure 7.4. I use this dummy neural network to simplify the visualization. Memory bottlenecks. 321. Figure 7.4. The forward and backward pass of a simple neural network. During the backward pass, each trainable parameter comes with additional values, its gradient, and its optimizer states. Therefore, the more trainable parameters there are, the more memory is needed to store these additional values. Memory math. It's useful to know how much memory a model needs so that you can use the right hardware for it. Often, you might already have the hardware and need to calculate whether you can afford to run a certain model. If a model requires 30 gigabytes of memory to do inference, a chip with 24 gigabytes of memory won't be sufficient. A model's memory footprint depends on the model as well as the workload and the different optimization techniques used to reduce its memory usage. Because it's impossible to account for all optimization techniques and workloads, in this section, I'll outline only the formulas for approximate calculations, which should give you a rough idea of how much memory you need to operate a model, both during inference and training. Inference and training having distinct memory profiles is one of the reasons for the divergence in chips for training and inference, as discussed in Chapter 9. 322, Chapter 7, Fine-tuning. 8. Some might say that you're not doing AI until you've seen a runtime error, CUDA out-of-memory error. 9. To learn more about inference memory calculation, check out Carol Chen's Transformer Inference Arithmetic, Kipley's blog, March 2022. Memory needed for inference. During inference, only the forward pass is executed. The forward pass requires MEMORI for the model's weights. Let n be the model's parameter count and m be the memory needed for each parameter. the memory needed to load the model's parameters is n times m. The forward pass also requires memory for activation values. Transformer models need memory for key-value vectors for the attention mechanism. The memory for both activation values and key-value vectors grows linearly with sequence length and batch size. For many applications, the memory for activation and key-value vectors can be assumed to be 20% of the memory for the model's weights. If your application uses a longer context or larger batch size, the actual memory needed will be higher. This assumption brings the model's memory footprint to n times m times 1. 2. Consider a 13B parameter model. If each parameter requires 2 bytes, the model's weights will require 13B times 2 bytes equals 26 gigabytes. The total memory for inference will be 26 gigabytes times 1. 2 is equal to 31. 2 gigabytes. A model's memory footprint grows rapidly with its size. As models become bigger, memory becomes a bottleneck for operating them. A 70B parameter model with 2 bytes per parameter will require a whopping 140 gigabytes of memory just for its weights. 9. Memory needed for training. To train a model, you need memory for the model's weights and activations, which has already been discussed. Additionally, you need memory for gradients and optimizer states, which scales with the number of trainable parameters. Overall, the memory needed for training is calculated as training memory equals model weights plus activations plus gradients plus optimizer states. Memory bottlenecks. 323. 10. To learn more about training memory calculation, check out Elutherai's Transformer Math 101, Anthony et al., April 2023. During the backward pass, each trainable parameter requires one value for gradient plus 0 to 2 values for optimizer states. Depending on the optimizer, a vanilla SGD optimizer has no state. A momentum optimizer stores one value per trainable parameter. An atom optimizer stores 2 values per trainable parameter. Imagine you're updating all parameters in a 13B parameter model using the atom optimizer. Because each trainable parameter has 3 values for its gradient and optimizer states, if it takes 2 bytes to store each value, the memory needed for gradients and optimizer states will be 13 billion times 3 by 2 bytes equals 78 gigabytes. However, if you only have 1B trainable parameters, the memory needed for gradients and optimizer states will be only 1 billion times 3 by 2 bytes equals 6 gigabytes. One important thing to note is that in the previous formula, I assumed that the memory needed for activations is less than the memory needed for the model's weights. However, in reality, the activation memory can be much larger. If activations are stored for gradient computation, the memory needed for activations can dwarf the memory needed for the model's weights. Figure 7.5 shows the memory needed for activations compared to the memory needed for the model's weights for different Megatron models at different scales, according to the paper Reducing Activation Recomputation in Large Transformer Models, by Korthakanti et al. 2022. One way to reduce the memory needed for activations is not to store them. Instead of storing activations for reuse, you recompute activations when necessary. This technique is called gradient checkpointing or activation recomputation. While this reduces the memory requirements, it increases the time needed for training due to the recomputation. 10.324, Chapter 7, Fine-tuning. Figure 7.5. The memory needed for activations can dwarf the memory needed for the model's weights. Image from Korthakanti et al., 2022. Numerical representations in the memory calculation. So far, I've assumed that each value takes up 2 bytes of memory. The memory required to represent each value in a model contributes directly to the model's overall memory footprint. If you reduce the memory needed for each value by half, the memory needed for the model's weights is also reduced by half. Before discussing how to reduce the memory needed for each value, it's useful to understand numerical representations. Numerical values in neural networks are traditionally represented as float numbers. The most common family of floating point formats is the FP family, which adheres to the Institute of Electrical and Electronics Engineers, IEEE, standard for floating point arithmetic. IEEE 754 FP32 uses 32 bits, 4 bytes, to represent a float. This format is called single precision. FP64 uses 64 bits, 8 bytes, and is called double precision. FP16 uses 16 bits, 2 bytes, and is called half precision. Memory bottlenecks 325. 11. Google introduced bfloat16 as the secret to high performance on cloud TPUs. 12. Integer formats are also called fixed point formats. 13. Range bits are called exponents.